Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hello and welcome to Hardware to Save a Planet. Our guest today is Robert Sansone, and I'm really excited about this episode because Robert is a little different from our previous guests in a couple of ways, at least. The first is that he hasn't yet started a company, and he's in the midst of the early hardware innovation process. His innovation is an electric motor for cars that could reduce both the environmental and financial costs of electric vehicles. The second way in which Robert is different is that he's a high school student. Robert began working on this motor design in his spare time as a junior at Fort Pierce Central High School in Florida. And then earlier this year, he won first place and $75,000 at the Regeneron International Science and Engineering Fair. So he stood on top of the podium at what's basically the World Championships of Science Fairs. And I think that is super cool. So Robert, welcome. It's an honor to have you here today. Thank you very much for joining us.
Yeah, thank you for having me.
So before we talk about the motor itself, I'd love to just get to know you better. How did you first get into engineering and making things?
Well, for my entire life, I've always kind of been a maker and a designer. I grew up on a farm, and my dad does work in like contracting and air conditioning repair. So, I've always been around an environment where we're always happening to come up with ways of fixing things and making things. And so I did that with my dad for the longest time. And, I'd take things apart, I'd repair things, figure out how things work. And I developed a passion for it. And so as I got older and started working on more complex projects and gaining more skills, I would push my skills as far as I can. And to this day, I still love engineering.
What are some of the can you give us some examples of some of the other projects you've worked on?
I've worked on a range of different projects. I've made 150-pound, four-legged running robots using lawnmower engines. I've made a pair of boots that they're kind of like stilts, and they allow you to run up to 22 miles per hour, which is Olympic level speeds. I've made go-karts that run 70 plus miles per hour. I've done a number of different projects over the years.
That's amazing. How do you choose what to work on?
I read a lot. I look at different videos. I kind of think of different things that I'd find interesting or be like, hey, that would be interesting to make. Or maybe nobody's seen that I've done this before, so I want to try this. So it's kind of wherever my interest takes me.
What's motivating you? Do you just love the process of engineering and making things and tinkering? Are you kind of more motivated by the end use of your inventions and what kind of impact it might have or how it might improve somebody's life?
I really like every part of the engineering process, all the way from, thinking of an idea to make, how I would come up with a design, to actually physically making the project. I really like every aspect of it. And then, of course, if the machine does do what I wanted it to do originally, then that's even better.
And so this show, we talk a lot about climate change and how hardware is impacting that. And your invention is definitely in that space, this motor invention that we'll talk about soon. What is climate change something you think about a lot, or does it just happen to be overlapping with this specific project?
Well, it does overlap with my electric motor research, but I guess if you look at some of the biggest problems, we see that climate change is becoming a bigger and bigger problem on humanity's list of things that we have to solve as we continue to burn fossil fuels. And so I have been concerned about the state of our planet going forward, and that played a lot into my electric motor research.
Mm-hmm. And outside of engineering and building things, what else do you do for fun? What else are you into?
Well, as I said, I live on a farm, so I kind of enjoy the outdoor lifestyle, like fishing and four-wheeler riding. And I usually find some way to combine that with the engineering that I do. That's pretty much what I like to do on my free time.
Can you tell me a little more about the farm? What's all on the farm?
It's mainly cattle ranching. So we have large pastures where cattle graze and exchanging cattle in the market and things like that.
Okay, nice. And you're in Florida, right?
Mm-hmm.
So could you just give a brief high-level description of what your invention is or what this motor is?
For the past year now, I've been working on my own novel design of a synchronous reluctance motor for use in electric vehicle applications, because the electric motors that are currently used in EVs, they utilize permanent magnets, which have rare earth materials that are very economically and environmentally unsustainable. And the synchronous reluctance motors have historically very low torque that's not suitable for EVs. And so with my design, I've been working on a way to improve their performance to be suitable for EVs without the rare earth materials.
How did you come up with the idea?
A little over a year ago, little before last summer, I was watching a video on like the advantages and the disadvantages of electric vehicles. And one of the major disadvantages that came up was the use of rare earth materials, particularly the electric motors that drive the electric vehicles. They utilize permanent magnets, which are like your refrigerator magnet, except they produce much stronger magnetic fields for higher performance. And they're able to do this because they utilize rare earth elements like neodymium and dysprosium. And these are a major problem because they have huge economic and environmental impacts. When they're mined, they're often found alongside radioactive materials like uranium and thorium. And so separating them you need very harsh solvents to do so, and it leaves behind a lot of radioactive waste. And then economically speaking, to refine the rare earth elements into permanent magnets, it's an extremely expensive process. So that makes the end cost very high. And most of the market is concentrated in China. And so it has a pretty unstable supply chain. And so, hearing about all these disadvantages, I was thinking we're trying to move away from the problem of fossil fuels to help fight climate change by adopting electric vehicles. But then we're kind of moving into this new problem with the rare earth materials. And so that got me thinking, well, why don't they use motors that don't use these permanent magnets? Like I knew from previous knowledge that the synchronous reluctance motor doesn't use any rare earth materials. And delving a little more into the research, I found out that the synchronous reluctance motor lacks the torque, that rotational force that the motor creates to move the vehicle. Its power to weight and torque density wasn't quite high enough for electric vehicle application. And so me being a maker, I started thinking of ways of improving the reluctance motor so that it can be used. And if it was used, it wouldn't have the environmental sustainability problems. And so that's kind of where my project got started.
So yeah, that's amazing that you identified that and then kind of pursued this path. Maybe just as kind of a baseline for everyone, can you describe how a conventional EV motor works relative to a synchronous reluctance motor?
Well, in electric motor, pretty much all electric motors have two primary parts, the stator and the rotor. The stator is it's usually the outer portion of the motor that's stationary. It contains a coil or a number of coils of wire. And when you pass an electric current through those coils of wire, it produces a magnetic field. And particularly for these EV motors, they produce a magnetic field that rotates inside the machine. And the rotor, which is the actual part that rotates the shaft, in a normal permanent magnet motor that they use in EVs, it has, permanent magnets laid on top of the rotor. And those permanent magnets produce a magnetic field that attracts to the rotating field that the stator produces. And that alignment with the rotating field causes the rotor to rotate as well. With the synchronous reluctance motor, it doesn't have any permanent magnets. And so how it produces torque is that it has a steel rotor and it normally has some shape of slots cut into it. So these air gaps that are created inside the rotor. And what this does is that it capitalizes on the principles of reluctance. Reluctance is essentially how easily a magnetic field can pass through a material. And something like steel that is magnetic has a very low reluctance. Magnetic fields can easily pass through it compared to something like air that is non-magnetic. So it presents a much higher reluctance or a harder path for the magnetic field to travel to. And these air gaps that are cut into the rotor, they're made in such a way so that if the rotating field penetrates the rotor at a certain angle or a certain axis, it presents a low reluctance path. It has a clear path through iron, which is low reluctance. But then if the rotating field hits it from another angle, it has to pass through those air gaps, which is very high reluctance. And magnetic fields always want to take the path of least reluctance, as this minimizes potential energy. It's kind of like a ball at the top of a hill. It wants to roll down to a lower energy state. And so the rotating field will move the rotor so that it's always aligned with that low reluctance path. And since the field is rotating, it continually produces that torque on the rotor.
The reason the synchronous reluctance motor has lower torque is because it doesn't have the same delta in reluctance between the steel and the air gaps as you get in an EV motor. Is that, am I understanding it right?
Well, the two motor types produce torque in a different way. With the permanent magnet motors, the torque is created from that actual magnetic attraction between the permanent magnets on the rotor and the rotating field that the stator creates. The synchronous reluctance motor produces the torque by the difference in reluctance between the two axes. So between the high reluctance axis and the low reluctance axis. The difference in reluctance between those two determines the torque. And that's actually called the saliency ratio, the difference in reluctance. And yeah, the saliency ratio currently is not high enough to exceed the torque that the permanent magnet motor can produce.
So that's how the two differ. And then can you tell me about what it is you're able to do with your change to a synchronous reluctance motor that enables it to have higher torque?
Well, as I explained, the torque is primarily determined for a constant power input. The torque is determined by that saliency ratio. And so, I was thinking, okay, if I want to maximize the torque, I need to maximize the saliency ratio that it's made. And normally the saliency ratio is made by the air gaps, the non-magnetic properties of the air gaps, and the magnetic properties of the steel. In doing research with this, I found that researchers, they've been looking at different shapes of the air gaps, different sizes, different steel grades to try and get better saliency. But ultimately, steel is only so magnetic and air gaps are only so non-magnetic. And so that ultimately limits the saliency ratio that you can create in the motor. And so what I was thinking is, rather than being limited by the material properties, I came up with a way of kind of introducing a different magnetic field to maximize the saliency ratio. And this is a potentially patentable machine that I'm still working on, so I don't want to get too much into the details, but essentially it maximizes the saliency ratio to get higher torque.
Can you tell me a little bit about the story of how you then have taken it through from that first point of identifying the problem and looking into it to the science fair?
Yeah, so I started it last summer, which was the summer before my junior year of high school. And when I started with the project, it was just something that I wanted to do for fun. I like making things, and I saw the problem with the rare earth materials. And I started thinking of different ways to improve the saliency of the reluctance motors. And I came up with an idea. And so I pursued that for most of the summer. I did lots of research, understanding better how these machines work. I made a few different prototypes to try and get like a proof of concept. And my first few prototypes failed. I kept going with the project, but then my junior year of high school started. And then it got a bit trickier because my schoolwork took a lot of my time away. And I was afraid that I wouldn't have time to work on it throughout the semester. Like I would have to wait till like this summer or something to continue working on it. But luckily, one of the classes that I was taking was a research class where the entire year is just devoted to conducting a study of your choosing and writing a research paper on it. So it's like, okay, this is a perfect opportunity to continue the work on my electric motor research. And so that was great. I was able to continue it throughout school because of that. And it was quite difficult to do because between schoolwork and stuff on the farm and working on the motor, I was working over 80 hours a week. But since I had the chance to do the research through my research class, I was thinking, okay, well, I wanted to do this project anyways. I'm doing it for my research class. I might as well make this a science fair project since I'm putting all this time into it. I'm familiar with the science fair from projects that I did in middle school. So I was like, I might as well make it a science fair project. And so, yeah, I brought it to my district-wide competition, my statewide competition, and I won best in fair and first place for both of those. And that advanced me to the International Science Fair, ISEF, where I ended up winning the competition.
I understand like winning a science fair is more than about the innovation itself. It's probably about how you present it the visual I have in my head is a big foam core poster board and you in front of that at a table with your motor. Is that, and judges sort of walking around an auditorium or something, but judging all these posters. Is that what's going on at these science fairs?
Yeah. At the Regeneron ISEF, you have people from all over the world. There was like 60 plus countries, and walking into this competition that was held in Atlanta, Georgia this year. When you walk in, there's like this huge exhibit hall where all the different projects are. And there's like, seeing this room, this exhibit hall was insane. There's like basically the top high school projects in the world presenting their research. And there was all kinds of different stuff in like every category of science and engineering that you could think of. And it was a little bit intimidating. I knew I did good research, but it was just amazing what some of my peers could accomplish. And so, yeah, I had my poster board. I didn't have really the resources to like have it printed out like some of the other students did. I kind of just like glue stick paper, like printed out papers. But I also brought my motor. I had a table with my whole setup, and yeah, you pretty much got it. There's different judges that go around. I think I had somewhere around like 10 or 12 judges come to my project. And a lot of students get like nervous presenting in front of the judges, but I kind of like the judging day. I got to talk about electric motors all day long.
Did you have any clue going into it that you would come out first place? Was that on your radar at all?
Well, of course I wanted to win the whole competition, but it was my first time ever participating in the international fair. So I wasn't really sure. And, after the judging day, I felt really confident about how I presented and how thorough my research was, but the competition was just so steep. So I really wasn't sure until, of course, the very end where I won.
Tell me about that competition a little bit. Do you remember some of the other entries?
Oh man, there was all kinds of stuff. There was like people making prosthetic limbs, quantum like levitation machines, and different computer algorithms for finding poachers in Africa. It was every kind of advanced research you could think of, like a student did it at this fair.
Beating a quantum levitation machine is pretty good. You should be pretty proud of that, whatever that is. That's amazing. And then did you win? Were you a celebrity? Were you handing out autographs? And what was that like? And I guess, did you know at the fair that you had won, or does it happen after the fact?
Well, the fair was a week long. It was like a Tuesday or something that the judging was. And then, there's a few days of different symposiums and activities and such. Then on Friday morning was the grand award ceremony. And that's when I found out that I won the competition. And it was a really surreal experience. You have all like the cameras on you and stuff. And there was a bunch of people asking for different media requests and interviews. And it just kind of all happens at once, and it's crazy. But it was good. And of course, when I got home, my family was super excited. My whole school was like, they had like this whole party for me coming home from Atlanta. It was great.
That's awesome. Maybe just back to the motor a little bit. I'd love to hear more about your development process. You're in high school. What sort of resources do you have access to that you use through this process? How are you doing your prototyping? What research are you doing? All that kind of stuff.
Well, to make my motor, I didn't have tons of different resources for making the machines, and they're quite complicated to make by hand. Electric motors are somewhat simple to make in a factory, but by hand is a whole other story. And so my primary resources was my 3D printer for making parts. And so I made all my prototypes. I made like the frame and some of the main parts out of 3D printed plastic. Then I wound the coils of wire in the stator by hand. And it was actually a quite lengthy process. Some of my prototypes had like upwards of like 10,000 coils of wire. And so each prototype took a tremendous amount of work to make. And in the beginning, I didn't know nearly as much about electric motors as I do now. And even now, I still don't know everything about how to design them. And so it took a lot of prototyping. And I didn't have a mentor to really help me when I had problems. So I would just make a prototype to my best intuition. And when it'd fail, I'd have to do tons of research and troubleshooting to try and see what went wrong. And if I couldn't correct the prototype, then I'd make another one. And I did this for several months. And I actually went through 15 versions of my electric motor before I got even a prototype that I could test to see if my design was working. it was disappointing to see all those different versions fail, but they didn't necessarily fail because of my design change. It was just because I didn't know as much about how to design electric motors, period. And so that kind of kept me going. I wanted a prototype that was good enough to prove my idea, whether it's right or wrong. And on the 15th version, I was able to get a prototype decent enough to do my experiments.
And is that the version you brought to the science fair?
Yeah, version 15.
I'm curious about the failures. I read a story about you that mentioned something about plastic parts melting due to high RPMs or something like that.
Yeah, since my motors were all 3D printed plastic, as the motor ran, it heated up and it actually began melting some of my earlier prototypes. I actually have this scorch mark on my desk from, I think it was version 10, that like completely failed because of too high of temperatures. So I kind of learned the hard way about adequate cooling in my designs. But even version 15, I had better cooling, but it was still 3D printed. It limited the RPM, or the rotational speed, that I could test my motor at to keep the temperature at bay. But I was able to get definitive results nonetheless for that speed range that I tested, which ended up being between 350 and 750 revolutions per minute.
How are you doing your cooling?
Well, most of my original designs didn't have any cooling system whatsoever. It was mainly like a closed-in design, which kind of trapped the heat. And version 15 didn't have any active cooling system, meaning it just dissipates heat out from its housing. And what I ended up doing to help with the cooling issue was I separated the coils so that I wrapped them in like this insulating tape so that they're not actually touching the plastic housing of the motor. And that helped it from overheating a lot. But still, it found a way to have issues. Like the heat would travel through the steel rotor and to the bearings that the shaft rotates on. And those bearings would heat up enough to begin melting the plastic that they sat in. And so it still limited the speed range that I could test my motor at. But with my continued research, I'm working on version 16 of my motor, and I have most of it designed on the computer. And yeah, version 16 definitely has an active cooling system, a fan that's actually blowing air across the coil so that temperature won't be as much of an issue.
And will you be able to change the materials, or are you still going to use your 3D printer?
Well, I don't have really a way of making it like an all metal design as most like commercial electric motors are made. Still going to use the 3D printed parts. But like I said, I'm going to add the active cooling system so that I can run it at higher speeds without it melting. And I also want to use different types of metal. The coils of wire are wrapped around these steel cores. And since the steel cores are magnetic, it helps concentrate the magnetic fields where you want them, which creates a stronger motor. But the problem is that the steel that I used was just like steel that I could get from like the hardware store. And so there's not really much specs available on the quality of that steel. And so if you have a bad quality steel for electromagnetic design, it actually ends up heating up a lot more. It creates what's called eddy current losses and hysteresis losses. And so that significantly limits the efficiency of the motor. And so with version 16, I'm going to try taking apart these transformers, which are electrical machines that like change voltages essentially. And so by cutting up a bunch of those, I can get that better quality steel that I'm going to use in my new motor.
What about the kind of analytical side of this? There's got to be some level of sort of modeling. Are you using hand calculations in Excel? Do you have some sort of simulation software?
Well, for my designing so far, I did all of my calculations by hand, which took a really, really long time, as one would expect. And I do all the calculations by hand. And then once I got something that I think would work, I designed it on a computer-aided design or CAD program that I would use to model it on the computer. And then I'd print out the parts that I would need. But now I'm moving into a phase where I have this company who reached out to me who are going to give me a student license for electromagnetic simulation software. So that rather happening to do all these calculations by hand, building a physical prototype, and then testing, see if it works or not, I can just design it all in my CAD program, import it to the simulation, and it'll tell me pretty much everything that I could do by physically experimenting, if not a lot more. And so once I get that, I'm going to spend time learning how to use that software so that version 16 and possibly future versions are a lot better designed.
You mentioned testing a little bit. What do the test results show? How does performance compare to, I guess, a typical reluctance motor or an EV motor that you're trying to replace?
Well, for my experiment, I designed version 15 of my novel synchronous reluctance motor, and I made the design modular so that it could be reconfigured as a more traditional reluctance motor. And in the speed ranges that I tested between the 350, 750 RPM, I was able to show over 30% increase in efficiency for most of the speed ranges and an almost 40% increase in torque compared to the traditional synchronous reluctance motor. And then since I made all my test equipment by hand, I made the motors by hand, I was worried about possibly, lurking variables that could have affected the results. So I also did a follow-up study where I isolated the theoretical principle under which my electric motor works. And I was able to validate that the improvements in torque and efficiency that I was seeing in my first experiment were in fact correlated to the design changes that I made and not some lurking variable.
So the ultimate goal, I guess, is to have torque that is comparable to the torque these permanent rare earth magnet-based motors can produce. Is there any way to estimate how close you are to that?
So far, I have not tested my novel design against the permanent magnet motors. I've only done it against the traditional synchronous reluctance motors. But based on some of the research I've done, the synchronous reluctance motor, the traditional design isn't too far from the permanent magnet motor. With advanced simulation techniques, some researchers have actually got them pretty high in torque. And so by able to improve that design by an additional 40%, I think I can get a motor that's comparable in torque to the permanent magnet design. But of course, that's going to take more testing with version 16 to know for sure.
What have been some of the biggest challenges you've come up against technically as you've gotten to this point?
Well, I guess the complicated part is, the main problem that I had was with the cooling, fighting with the cooling due to the 3D printed parts. That was very challenging, as I talked about before. And I guess another part was dealing with the electromagnetic design. So there's lots of calculus-based problems that have to do with how the magnetic fields travel through the motor. And doing that by hand was a bit of a nightmare. Some of the calculations I actually couldn't do by hand. And I didn't have a mentor to help me either. So navigating those higher level calculations with my prototyping was a bit tricky.
What level of math are you taking in school?
Currently, I'm in multivariable calculus and vector-based calculus, but I've taught myself pretty far on my own, upwards through differential equations.
Is that because you've been using differential equations in your motor design?
Yeah, I do some differential equations for my motor design. Lots of vector calculus go into the different laws of electromagnetics.
So as you look at prototype 16 and maybe future versions, what are the big challenges you're trying to tackle with those, or what are the big improvements you're trying to make with those, aside from the cooling that we already talked about?
When I originally came up with my advanced synchronous reluctance motor design, there was 3 primary changes that I wanted to make. And I made one of those changes in version 15 that I brought to the international fair. And I was able to show those improvements in torque and efficiency. But for it to actually be utilized in electric vehicle applications, there's more factors than just torque and efficiency that electric motor engineers look at. They look at many other factors like power factor and torque ripple, for example. And so the motor has to perform well in those respects as well. And so with version 16, I'm adding some of the other design changes that I had in mind to address those other factors, particularly with the torque ripple, because there's different ways of designing the coils of wire in the stator, and some of them are easier to manufacture than others. And so I wanted to use what's called a concentrated winding, where the coils are wound in their own independent coils rather than all distributed and woven together, which is called a distributed winding. That's typically used in the electric motors. And I wanted to do that for the cheaper manufacturing. But that also adds in the issue of torque ripple, which means that the torque is inconsistent. It's not a constant torque as it rotates. As the rotor moves closer to the individual coils, there's a loss in torque and then another spike in torque when it goes towards the next coil. And so a lot of version 16 is working out how to minimize the torque ripple so that I can use concentrated windings and still have good performance and manufacturability.
How's your confidence level in achieving that?
Well, I've had a lot of failure in my research before I got version 15 going. And so there's probably a decent chance that version 16 may not pan out how I think it is. But I have been working a lot more diligently with version 16. I've been working on it for almost over 3 months now, rather than the 3 weeks that I did between prototypes in my original study. And I also know a lot more about electric motor design, even when I finish version 15. And so I think that will definitely help me where I don't have to go through as many prototypes to prove my concepts. And then, of course, once I get going with the electromagnetic simulation, I think I can get it pretty nailed down if my design will work before I actually make it.
And do you have more access to mentors and technical support and resources and things now with your newfound fame?
Yeah, since recently after I won the international fair, I started a LinkedIn profile and I was able to reach out to like different electric motor designers and engineers. And so, yeah, now I'm definitely better equipped for moving forward with version 16 of my design.
Shout out to your LinkedIn profile, by the way. People should check it out. It's pretty fun because Robert posts videos of some of his other inventions as well, which is really cool to see. Just curious to talk a little bit about the potential business side of this. And I don't know, does the business side of this interest you as well as the engineering side?
Well, my main passion is for engineering, not necessarily business or entrepreneurship. And so moving forward with potentially implementing my design commercially, the kind of, I guess, steps there would be is finish version 16 or future versions to further prove my concept. And once I can show that it both has enough performance and is economically viable, then I'd move forward with the patent process. And with a patent, I would be able to license it to different companies, which is essentially allowing permission for them to utilize my design in exchange for something like a royalty. I'd rather go that route so that I can continue what I love, which is making things.
What's kind of between you and patenting it right now? What steps do you have to go through?
Well, patenting is a somewhat expensive process. And so I don't want to just throw a bunch of money into this until I know that I have something that can actually be used in electric cars or another similar application. And so I really want to do more thorough testing with my design and make sure that it's commercially viable, that has good performance. And then, of course, if all that goes well and I think it is worth patenting, then, go forward with provisional patents, which is like the initial stage in the process. And then the entire patenting usually takes a little over a year to do.
What's something you've learned through this process that you wish you had known going into it?
I guess the main thing that I wish I would have known, it goes back to that cooling. I mean, I was well aware that electric motors need adequate cooling, but I did not think it was going to be that much of a problem. I swear, like a half a dozen of my motors alone just had the cooling problem. And so if I would have known that the cooling would have been so much of an issue before, and I guess I should have known this, especially with like 3D printed parts, but if I'd known that before, I would have definitely added a cooling system before. That was the main thing I wish I would have known.
And I guess that just thinking through this, you're doing this during COVID. So are you testing all these in your house?
Yeah, I have a little shop on my property where I do all my building.
Okay, so when you're melting plastic and burning desks and things, it's not necessarily pouring fumes into the house. It's just contaminating your workshop.
Yeah, pretty much. And yeah, cleaning up after melted plastic isn't always fun.
Your parents must be supportive, though.
Yeah, they're very supportive. They kind of just let me go and build the things that I want to do. And that's, I think that's the best way of learning, doing it hands-on and seeing it for yourself when things go wrong.
So I need to caveat this next question by saying that I personally still don't know what I want to be when I grow up. And I think that's totally fine. But I am curious if you have a sense for what you want to do after high school and college.
Well, I obviously want to pursue engineering. I'm interested in kind of energy conversion and energy management. So particularly like energy conversion, like electric motor design And I also take interest in like energy storage. So like batteries, supercapacitor technology, different ways of managing like our energy grid, things like that. And so ultimately I want to get into electromechanical systems. And so I'd like to pursue, a bachelor's degree. I would like to go to MIT. That's my dream university. And they have this course 2A program where it kind of combines electrical and mechanical engineering together so that I can kind of focus on that electromechanical type engineering, which is what I'm most passionate about.
That's a really interesting space, I think. A few closing questions. How optimistic or pessimistic are you about the future of our planet and why?
I guess I would say I'm kind of both pessimistic and optimistic. And what I mean about that is like in the short term and in the medium term, as far as our switch to fully sustainable energy, I kind of have a pessimistic feel because I don't think that humanity is moving fast enough to fully not face the consequences of climate change. I think that we will in these upcoming decades have some environmental issues. Even today, we're seeing some of the effects of climate change, disturbances in weather, global temperature, and sea level rises and things like that. And I feel like as we're trying to move forward with sustainable energy, we're definitely going to see those consequences in a much more severe fashion. But even though humanity is really good at finding ways to destroy itself, basically, I think humanity is very good at getting ourselves out of problems. And so I think our next generation of innovators, myself included, I think we can come up with technology to pull through. And as the environmental consequences get more severe, I think the government organizations will be more keen on working towards resolving the issue. So, overall, I think we're going to see the consequences. Worst consequences from climate change are coming, but I think we'll be able to pull through before the planet becomes like inhabitable.
Is there one other person or invention or company you're aware of that's addressing climate change that's inspiring you?
Well, with my work with electric motors, I'm obviously drawn more towards like that lens when it comes to climate change. So yeah, there's a lot of companies that are working with motors that don't use permanent magnets. Particularly one that I find inspiring is Turntide Technologies. They're one of the leading companies for designing actually reluctance motors. Their mission is to create motors with higher efficiency because a good 30-40% of all the electricity that we produce every year is consumed by an electric motor. And so by improving their efficiency, we'll be able to minimize a lot of the energy that's produced. And of course, that would help with climate change. And the reluctance motors that Turntide is doing is not only more efficient than most of the alternatives, but they also don't utilize the permanent magnets, which is kind of in a similar space that I'm in. And I find that company particularly inspiring for me.
Cool. I'll check them out. Are they also targeting the EV space?
Primarily, they look at like HVAC, like air conditioning applications and like small commercial industrial application, because that's where most electric motors are found and used. And that's most of the motors that consume our electricity that we produce. But I've seen, with some of their new research that they are producing motors that could potentially be used in EV applications and similar to hopefully what I aim to do with my own design.
What advice do you have for other people your age who want to do something about climate change?
I guess my primary advice to my peers in that respect would be don't wait. I mean, if you're passionate about engineering or science pertaining to climate change, you don't have to wait till college or a career to start having an impact. I mean, I didn't have tons of resources for making things, but I was creative about it. I was really passionate about what I did. And I was able to end up making a pretty good electric motor that could help with this crisis that is going on. And even if you don't create a world-changing machine, as like a teenager, and there's still no guarantee that even my electric motor design would have that sort of impact. But getting started early, definitely, you learn a lot from doing these kinds of projects so that when you do enter college or a career, you and our generation as a whole will be better suited for fighting humanity's challenges.
Well, Robert, you've set that example really well. And it's been really fun to talk to you. I'm impressed and inspired by your creativity, your initiative, all the hard work you've put in, and just how articulate you are about it. It's really cool to meet you and to talk with you. And I appreciate all of your time. Thank you.
Thank you for having me.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, and Google Podcasts, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.